So am I audible to all of you? Am I audible to all of you?
Yes, sir.
Okay. So today we will discuss about the analysis of structure, the basic things. Okay. So a beam is a structural member that is designed to support the applied load, and it resists the applied load by a combination of internal transverse shear force and bending moment. So it is the perhaps it is the most important and widely used structural member. Now all of you know in the last classes we have discussed regarding the introduction, what is the beam, types of support, types of loads and all, right? So today we will see how to analyze a beam. Okay. Now let us revise a bit. There are different types of beams as you all know. Number one is cantilever. So what is a cantilever beam? A beam which is fixed at one end and free at the other end. It is known as what? A cantilever beam. Okay. That means what? You can see this particular beam. This is what fixed in this side, right? This is fixed in this side, and it is free in this other end. So this is why it is known as a cantilever beam. So these are certain examples of cantilevers. Look at this. It is fixed here, right? So if it is fixed here, then it is projecting outside, right? So this is a cantilever for concrete, and this is what? This is also a cantilever. Why? This is made up of steel, right? So it is a cantilever for steel. Then simply supported beam. So the basic example of simply supported will be what? Suppose there is a stream or something like that. Now for passing through the stream, what people do sometimes is what place a log of wood which connects both the end of the stream. So that connection is basically known as what? A simply supported beam. Okay. Don't give your attendance now. Why you are giving your attendance now? I won't consider this an attendance. Achumi and Sissi. So after that, if you go to the next, fixed beam. Fixed beam you all know. It is fixed in both ends. I showed you one video also in the last class for the fixed beam. Okay. Then we go to the next, overhanging. So what is actually overhanging beam? The overhanging beam has what? Supports at one end, and it is what? Overhanging in other end. If you can see this one, so this is called an overhanging beam. Then continuous beam. So now we'll go to the types of load. So what are the different types of load? First of all, concentrated load that is assumed to act on a point. So these all are concentrated loads. That means what? Suppose this is a beam, right? This is a beam. So what happens is that in the beam the loads are what? Acting at only one point. So these are all what? Concentrated load. Because these are acting only in this point and this point, right? Then you have uniformly distributed load or UDL. We generally call it as what? UDL. This is uniformly distributed load. That means what? This type of load is distributed in the entire section of the beam. Okay? This is called uniformly distributed load. Then uniformly varying load. Look at this picture. If you can see here, the load is zero at this point, but it goes on increasing and all. It reaches to the maximum level at the other end. That means what? This is uniformly varying. So this type of load is called what? Uniformly varying load. Okay. Now we'll go to the next. What does loads do actually? Now we also studied in the first class, initial classes, right? Shear, shear force, shear, causes shear, and then all thing, right? Now look, these loads might result in what? Either bending or shear. Now suppose this is a beam. Look at these white patches, these dotted lines. So if you place the load here, so then this will cause the load to what? Bend. This is a simple example you can think. If you take a stick of wood, then place it in the middle of it. It will bend like this, right? That is what the load does actually. Then for shearing, what happens? If the load is applied, forces are applied from both sides. So you can see this diagram. Then what will happen? The beam will tear off, like you tear a piece of paper. Hmm? So it will tear off, and this is called shear. Now, what is the importance of designing of buildings? So the importance of designing a beam. Your friends, what they do is like they all enter after the class starts. It becomes very difficult for me. Every time I have to stop sharing the content and then admit them again and again. So, designing of beams. This is what is important. Now, beams are very important for designing. Why? Because so that to assess or to ascertain so that the structure that you have made is actually stable or not. So, beams in a building are designed for bending and are checked for what shear. Now, this is a very important part. First of all, try to understand. So, how do you calculate actually the effect? First of all, we have to find all the forces, that is the loads and the reaction. So how to find out the loads and the reaction? We'll have to see. You have to see, like this. Suppose this is a. Try to understand. Okay, this is a point load. And this load is acting on this simply supported beam. So how to analyze this beam? First of all. So first of all, you have to find out what reactions using conditions of equilibrium. Do you know how to find out the reactions? The last semester we discussed, I think so. You know how to find out the reactions? Can anyone say me? Can anyone unmute and say me?
For what, sir?
Huh? Yeah, say me. Do you know how to find out these reactions? Do you know?
No,
Don't know, na?
no.
So let us
For
discuss
that,
on it. Okay, okay, no problem. Let us discuss. So now, how to start a study? First of all, this is the load. This is the point load that is acting at this point. Now, suppose this is a 5 kilonewton load. Now, I have to explain you one thing. The important thing is what? Span. What is a span? The distance between the two supports. If it is 5 meters, suppose. So this is called the span of the beam. Just remember one thing. This distance between the supports is called the span of the beam. Now let us consider this point as A and this point as B. So what will happen? From Newton's third law of motion, we all know every action has an equal and opposite reaction. Now the action here it is what? This is in the form of this load. Huh? This load. So this load is how much? 5 kilonewton, right? And so the opposite reaction will be given by these two supports, this one and this one. So we'll be having two support reactions, RA and what? RB. Now, how to find out this RA and RB? Now, from conditions of equilibrium, we all know this one is the basic condition of equilibrium from Newton's third law of motion. RA into 5 RA into 5 means force into perpendicular distance, that is the moment, is equal to what? It will be equal to how much? It will be equal to how much? It will be equal to how much? Now let us think that this distance, that is the load and the end support distance, is 3 meter. So we are finding out the moments about point B, that is RA into 5 equal to what? 5 into how much? 3. Because this one, force into perpendicular distance, is the force into perpendicular distance is the moment. So 5 into 3. Now cancel this and this, we get what? RA equal to 3 kilonewton. Now we all know RA plus RB equal to how much? 5 implies RB equal to how much? We all know now RA is how much? RA is 3. So we can write here 3. That means what? RB equal to 5 minus 3 equal to how much? 2 kilonewton. That's it. I hope it is clear for all of you. Is it clear for all of you? Is it clear for all of you? Someone unmute and respond. Is it clear for all of
Yes, sir.
you?
Yes, sir.
Oh, okay, okay. And what about others?
Yes,
Yeah,
sir.
two, three people have responded. So many people are there. Why no one respond? What about others? Did you get it? Yes? Okay, good. Very good. So, this is what the basic concept of finding out the reactions. Now we'll go to the next one.
If sir, it the diagram is in cantilever.
First of all, let us go from the basics, right? If your basics are not clear, then your main concept will only not be clear, right? We'll be going from basics.
No, sir. First, how we find out the reaction of the cantilever
Do you understand what I'm
beam?
saying you? Let us go from the basics. We'll go eventually to all the others. Is it clear?
Yeah, it's clear.
If your basic is not clear, then पूरा पुर्जा हिल जाएगा, गिर जाएगा तुम उसके बाद. So first, let us go from the basics. First, simply supported, then we'll go to cantilever, step by step. Clear? So this reaction part, I think so it is clear. Now I'll show you one video. Then your concept will be a bit more clear.
Example, we are looking at a simply supported beam. As you can see, it is a 5-meter long beam, and we have 15 kilonewton load applied at B. Distance from A to B is 3 meters, and from B to C is 2 meters. It is simply supported with a roller support at this end. We only have one vertical load applied onto the beam at B. Hence, we would only have vertical reactions at A and C. If I note them as RA and RC, then we can begin our calculations to determine the reactions at supports. What I'm going to do is take moments about A. You can see that the lever arm is 0 for reaction RA when you're taking moments about A. Hence, RA has 0 moment about A. We have an anti-clockwise moment due to RC reaction, and the lever arm is 5 meters. It's from A to C. So we can write moments about A are C times 3 plus 2. RC is causing an anti-clockwise moment. As you can see, would try to rotate this beam in this direction anti-clockwise. And then we have this 15 kilonewton force acting at B, which is causing a clockwise moment. It would try to rotate this beam about A in this direction. So we can write this is equal to 15 times the lever arm 3 meters. You can write 5 RC is equal to 45 and RC is equal to 9 newton. Then we can take moments about C. Just like before, the lever arm is 0 for reaction RC when you are taking moments about C. Hence, RC has 0 moment about C. Then we have 1 clockwise moment due to reaction RA, and the lever arm is 5 meters. Moments about C. RA times 2 plus 3, and we have this 15 kilonewton force causing an anti-clockwise moment about C, and the lever arm is 2 meters from this point to B. This is equal to 2 times 50. We can write 5 RA is equal to 30 and RA is equal to 6 kilonewton. Now what we need to do is undertake a check of vertical equilibrium to make sure that the results we derived are correct. You can write vertical equilibrium. For vertical equilibrium, when you add these two reactions, RA and RC should be equal to 15 kilonewton. You can write RA plus RC is equal to 9 kilonewton. 9 kilonewton plus 6 kilonewton is equal to 15 kilonewton, and that is equal to the applied force. So the results we derived for RA and RC reactions are correct. If you like the video, please
shear force and bending moment diagram. Shear force and bending moment diagrams are powerful graphical methods that every mechanical and civil engineer should know how to use to analyze a beam under loading. In this video, I'll explain exactly how to master these diagrams, and we will see how they can be used to understand how a beam is loaded. I want to start by explaining what shear forces and bending moments actually are. When a beam is loaded, internal forces develop within it to maintain equilibrium. These internal forces have two components. We have shear forces, oriented in the vertical direction, and we also have normal forces, which are oriented along the axis of the beam. If the beam is sagging, the top of the beam will get shorter, and so the normal forces in the top of the beam will be compressive. The bottom of the beam will get longer, and so the normal forces in the bottom of the beam will be tensile. Each of the tensile normal forces has a corresponding compressive force, which is equal in magnitude but opposite in direction. As such, these forces don't produce a net normal force, but they do produce a moment. This means we can conveniently represent the internal forces acting on the beam cross-section using just two resultants. One, shear force, which is a resultant of the vertical internal forces, and one bending moment, which is a resultant of the normal internal forces. This is a very common way of representing the internal forces within a beam. Drawing the shear force and bending moment diagrams is just figuring out what these internal forces are at each location along the beam. These resultant shear forces and bending moments will depend on the loads acting on the beam and the way in which the beam is supported. Beams can be loaded in a number of ways, the most common being concentrated forces, distributed forces, and concentrated moments. Beams can also be supported in a number of different ways. They can have pin supports, roller supports, or be fully fixed, which each restrain the beam in different ways. Pin supports prevent vertical and horizontal displacements, but allow rotation. Roller supports prevent vertical displacements, but allow horizontal displacement and rotation. Fixed supports prevent all displacements and rotation. If a certain degree of freedom is restrained at a support, we will have a corresponding reaction force or reaction moment at that location. For example, rotations are permitted for a pin support, so there is no reaction moment, but displacements in the vertical and horizontal directions are prevented, so we will have horizontal and vertical reaction forces. So how do you determine the shear forces and bending moments within a beam? There are three main steps we need to follow. First, we draw a free body diagram of the beam. This shows all of the applied and reaction loads acting on the beam. The next step is to calculate the magnitude of the reaction forces and reaction moments at all of the beam supports. We do this using the concept of equilibrium. To maintain equilibrium, all of the forces in the vertical and horizontal direction should cancel each other out. Similarly, all of the moments acting at every point along the beam should cancel each other out. This gives us a set of simple equations we can solve to calculate the reaction forces and moments. If we can calculate all of the reaction loads using the three equilibrium equations, the beam is said to be statically determinate. For some beam configurations, like this one shown here, we won't be able to calculate all of the reaction loads because we have too many unknowns and not enough equilibrium equations. In this case, the beam is said to be statically indeterminate. This beam has 4 reaction forces, but we only have 3 equilibrium equations. To solve this beam, we would need to use slightly more complicated methods and consider boundary conditions. In this video, I will only cover statically determinate cases, where we can use the equilibrium equations to calculate all of the reaction loads. Once we have calculated all of the reaction loads, the third and final step is to figure out the internal shear forces and bending moments at every location along the beam. To do this, we will use the concept of equilibrium again. If we cut our beam at any location, the internal forces and moments need to cancel out the external forces and moments so that equilibrium is maintained. This allows us to easily calculate the shear force and bending moment at each location along the beam. All we need to do is start from one side of the beam and move the location of the cut along the beam, calculating the shear forces and bending moments as we go. Now is a good time to define the sign convention we will be using. Applied forces will be positive if they are acting in the downwards direction. For shear forces and bending moments, the positive sign convention will be as shown here. If the beam is on the left side of our cut, shear forces pointing downwards will be positive. If the beam is on the right side of our cut, shear forces pointing upwards will be positive. Positive bending moments will be those that put the lower section of the beam into tension. Another way to think about it is that bending moments which cause sagging of the beam are positive, and those that cause hogging of the beam are negative. Let's take a look at an example of a beam with pinned and roller supports, loaded by two concentrated forces. First, we draw the free body diagram. We can then use the equilibrium equations to determine the unknown reaction forces at point A and point B. The sum of the forces in the vertical direction is equal to 0, so RA plus RB is equal to 15 plus 6. Because HA is the only horizontal force, it must be equal to 0. We also know that the sum of the moments about any point along our beam must be 0. Let's consider the moments about point B. That gives us this equation, which we can solve to determine that RA is equal to 12. By substituting RA into the previous equation, we can deduce that RB is equal to 9. Now that all of the external loads acting on the beam are defined, we can draw the shear force and bending moment diagrams. We will start from the left-hand side of the beam. Let's draw the free body diagram for a location immediately to the right of the 12 kilonewton reaction force. To maintain equilibrium, the shear force must be equal to the reaction force. We can draw this on our shear force diagram. The shear force will be constant until we reach the next applied force. The bending moment must be equal to the 12 kilonewton reaction force multiplied by the distance x to the reaction force. This gives us the equation for a straight line, which we can draw on our bending moment diagram. We then repeat the process by moving the location of our cut further to the right. This time we place the cut immediately after the 15 kilonewton force, and we draw the free body diagram again to determine the shear force and the bending moment. We repeat this process until we have covered the full length of the beam. We end up with the complete shear force and bending moment diagrams for the beam. That example was a fairly simple one. For cases with more complex loading, drawing the shear force and bending moment diagrams can be more difficult. There are relationships between the applied loads, shear forces, and bending moments.
I hope it is clear up to this part for every one of you.
Sir, can you send the link of this video?
Yes, what do you say?
A link of this video, sir. Send us.
Okay. Let me see. You just look to the half part, okay? That is why I could not find the link actually. Wait, I'll find it and send it to you. Give me a minute. We'll discuss about it in the next class in details. I've sent you the link in the chat box. Also, you can see my class videos today. You can find out it up to there also.